What's up, guys? First video on a new topic. We're going to look at Equilibria this topic, and we're starting off with this idea of a dynamic equilibrium. Before we get started though, please like, subscribe, share to anyone you think this might be helpful to. Let's keep growing the channel. Let's get into it. So first thing, we need these key terms. So first of all, a closed system. So it's a system where nothing can enter or leave. So there, we might be talking about something like, a conical flask with a bung in it, so that whatever the reaction going on here, nothing can escape, no gases could escape, and we're not going to enter anything into it either. So it's a closed system. So a dynamic equilibrium, next term, is where we have a forward and reverse reaction occurring at the same time and pace. And rates. So there we're generally denoting this. It's possible for any reaction where we get this symbol. So this symbol talks about a reversible reaction. Normally we obviously get this kind of thing. And we have a dynamic equilibrium whereby the reaction of the forwards and the reverse are happening at exactly the same rates. Okay, hopefully some examples will make that a bit clearer. Now also at that same time, concentration of products and reactants stay the same. Now, when I say that, I don't mean they're the same as each other. What I mean is they stay the same. So if this is 12 and this is 2, this will stay 12 and this will stay 2. They don't need to be the same concentration of each other. And this final thing, Le Chatelier's principle, is this idea that a reaction will shift to counteract the effects of any imposed change. And what I mean by that, if we make the conditions warmer, the reaction will shift to make it cooler again. If we increase the pressure, the reaction will shift to try and decrease it again. So it's sort of, and this is why we call it a dynamic equilibrium, because it can change, okay? So let's look at an example. So for starters, we know this is a reaction where equilibrium can happen because we have this reversible reaction symbol. It's got A plus B makes C plus D. Now we're told, and often you're told, what the forwards reaction energy change is. So obviously this is going to be in kilojoules per mole. And because it's positive, we know that it's an endothermic reaction. Therefore, the backwards reaction is going to be the opposite. It's going to be exothermic. And it would also be exactly, right? So minus 50. That's why things like Hess's cycle work, because the forwards is equal and opposite to the reverse. Now, what does that mean? Here, if we increase the temperature, the reaction's going to shift to try and decrease it. So in that case, the endothermic is going to absorb the extra heat energy. So if we increase the temperature, reaction shifts right. So it moves from this side to this side, which means more And we can say because forward reaction is endothermic. And we can also say, therefore, yields of C and D increases. So, if we go the other way, if we decrease the temperature, the opposite happens, right? So if we decrease the temperature, the reaction would shift left because the backwards reaction is exothermic, therefore yield of A plus B increases. Right, so this would be sort of interchangeable. We can also think about what would happen if we increase the pressure. So if we increase the pressure, there we need to think about moles of gas. So on the left-hand side, we have 2 moles of gas. On the right-hand side, and there we're looking at the big numbers. So if this had a 2 in front, we'd say it had 3 moles of gas. And here we've only got 1 mole of gas because D is a solid, right? So if we increase the pressure, the reaction will shift to the side with fewest moles of gas. And very simply, that's because this is going to take up less space, right? So if we increase the pressure, reaction shifts right. Because there are less moles of gas. And we might even say 2 to 1, right? Reaction shifts right because there are less moles of gas. Therefore, yield of C plus D increases. And we can go the other way. So if we decrease the pressure, reaction will shift left because there are more moles of gas, 2 to 1, yield of A plus B increases. Now, final thing that's worth us knowing. Let's make this a bit smaller so we can fit. Is if we increase the concentration of anything. So say if I increase the concentration of A, what's going to happen there? There, because we've increased Le Chatelier's principle, the reaction shifts to counteract that change. It shifts away to reduce that number of moles again. So there, reaction shifts right again. And because forward reaction. To reduce concentration of A. We can say, therefore, yield of C plus B increases. D increases, sorry. Perfect. So, now let's look at a couple of real-life examples. So we can start off with the Haber process. So a lot of the times, we're sort of thinking about how can we increase the yields. So we want highest yield of NH3. So we think about the conditions, right? So we can see, first of all, the forwards reaction is exothermic, right? So because of that, cold conditions will shift the reaction to the right. So we can start off we're saying low temperature as forwards reaction is exothermic. So reaction will shift to the right to counteract the change. And then we can think about what we need to do to the pressure. If we look on the left-hand side, we've got 4 moles of gas. And on the right-hand side, we've only got 2 moles of gas. So therefore, we want as high a pressure as possible. So high pressure as there are fewer moles of gas on the right hand side. So reaction will shift right. And we can even say 4 to 2. So reaction shifts right. Perfect. Last one. So again, we can think here about how we can produce as much NO2 as possible here. So there, we're thinking about this. So first of all, highest yield of NO2. Hopefully you've got a sort of general idea of what we're expecting here. So first of all, what do you think? Have a little think. What conditions might we need? We've got positive energy change here. Think about moles of gas. What are we going to need to do to pressure and temperature? Have a little pause, have a little think. Okay, so first of all, we have positive energy change, so we know it's an endothermic reaction. So, first thing, high temperature. And we need to stipulate as forward reaction is endothermic. So reaction will shift right. And hopefully you worked out pressure as well. We've got 1 mole of gas here, 2 moles of gas here, so low pressure. As more moles of gas on right hand side. So reaction shifts right. And you might have talked about as well, increasing the concentration of N2O4. Again, we'll shift it to the right. Your turn. So, give these a go. Again, sort of general random examples here. Again, think about the sort of terminology we've used all the way through. That's it for this video. I'll see you next time. Until then, happy revising, guys.